Okay, so in the last lesson we talked about how to predict how many signals a given compound would produce. In this lesson we are going to predict where those signals will appear along the x-axis, and if you recall, that's called the chemical shift. So chemical shift refers to position of a signal along the x-axis. And these values are in units of ppm, and they typically range from 0 to 10. And if you remember, these measurements, 0 to 10, are determined by the chemical environment of the proton. So if a proton is in a very electron-rich environment, it's said to be very shielded, and so its ppm value or chemical shift value will be close to 0. However, if that proton has very little electron density around it, then it's said to be deshielded, and the ppm value or chemical shift value for that proton will be closer to 10. So let's take a look at a very clear-cut example of how this effect manifests. So let's just take a look at the simplest case organic compound, which would be methane. And if you look at the protons in methane, they're all equivalent. They're all going to generate one signal because they're all symmetric and they're all in the same chemical environment. And so the ppm value for those protons in methane is 1.0 ppm. All right, beautiful. So that can be kind of our baseline level there. Now let's replace one of the hydrogens in methane with an electronegative halogen atom. So I'll just put one of the hydrogens and replace it with iodine. How do you think this is going to affect the chemical shift of those protons? Well, the iodine is an electronegative element, which means it sucks electron density towards it through an inductive effect. Remember, we talked about inductive effects. So that's actually going to reduce the electron density on the carbon, pulling electron density away from the carbon, which in turn is going to reduce the electron density that the hydrogens have. So that is going to deshield the hydrogens, and sure enough, the ppm value increases to reflect that up to 2.2 ppm. So a pretty dramatic shift. Now let's replace the iodine with a chlorine, or let's do bromine first, which is a little bit more electronegative than iodine. So if we replace the iodine with bromine, we should expect even more deshielding because bromine is more electronegative. And indeed, the value is now 2.7 ppm. It increased because the hydrogens are even more deshielded because even more electron density is sucked away from them by the electronegative atom. We can go one step further. We can replace the bromine with a chlorine, even more electronegative. And now we're down to, or up to, 3.1 ppm, even more deshielded. And why not go all the way? We can install a fluorine instead, which is the most electronegative halogen, most electronegative atom actually, and that pulls us all the way up to 4.3 ppm. So here you can clearly see, as we remove electron density away from the hydrogens, the chemical shift value for those protons increases as they become more deshielded. And the effect is additive. The effect is additive. So if you look down here at this example, as we add more and more chlorines, we would expect there to be increasing deshielding. And sure enough, we see that. So for the first example, we have 1.0 ppm. With one chlorine, we go to 3.1 ppm as we saw above. With two chlorines, all the way up to 5.3 ppm. And with three chlorines, we're at 7.3 ppm. So each chlorine adds approximately 2 ppm to the proton's chemical shift because each chlorine sucks yet more electron density away from the hydrogen and thus causing it to be highly deshielded. Now it's interesting to note that the effect tapers off with distance. So let's take a look at this compound here. This is propyl chloride, and let's just draw in all the hydrogens. I'll just draw in all the implicit hydrogens here. And as you get further away from the chlorine, the inductive effect becomes less and less strong. So the first two hydrogens, which are really close to the chlorine, those show up at 3.3 ppm. But now if we get another carbon away, the effect is not very strong, and those appear at 1.6 ppm. And then by the time you get three away, the effect is pretty much not felt at all, and these are all the way down to 0.9 ppm. So the effect is distance-based. The more bonds you have to go through, the less the inductive effect can play a role. Okay, so this is all well and good. This is sort of a trend, but are we able to actually predict these values? Yes and no. I'm going to give you a limited set of rules that will allow you to predict common chemical shift values for protons. So let's take a look at the next page and see. I'm going to start by giving you some base values, and then you're going to add to these base values some modifiers. So it's kind of like a game, right? You have this base level, and then you're going to assess and look for modifying functional groups that are nearby, and then you're going to add to the base value. It's kind of fun. So let's take a look. There's 3 base values to know. The first is the methyl group. Methyl is referring to a carbon with 3 hydrogens on it. So CH3 is a methyl group. You guys know that. And the base value for a methyl hydrogen is 0.9 ppm. We're going to set that as our base value. The next type of hydrogen I want to tell you about is called methylene. Methylene is similar to methyl. I'm just drawing these little squiggly lines to show that there's stuff connected. I'm not specifying what it is. Methylene is a carbon that has 2 hydrogens attached. So this is called methylene. And the base value for a methylene hydrogen is 1.2. Okay, and the final type of hydrogen we'll consider for our base values is a methine hydrogen. That is when you have a carbon that has only 1 hydrogen attached to it. We're going to call that methine. And the base value for methine is 1.7 ppm. Okay, so just keep these base values in mind. Oh, I was supposed to write that in blue. My bad. Keep those base values in mind as we look now at some modifiers. Okay, the first modifier is a very powerful modifier, and it is an oxygen of an alcohol or ether. And when we talk about these modifiers, this means next to this functional group. And so if you have a hydrogen that's on a carbon next to an oxygen of an alcohol or ether, the effect is a whopping plus 2.5 ppm to the base value. Let's take a look at an example. Okay, here's ethanol, and let's draw in the hydrogens that are next to the alcohol. Okay, so these are the hydrogens not directly attached to the oxygen, but on the carbon that is next to the oxygen. And so now let's calculate its predicted chemical shift value. So what type of carbon is this? What's the base value of those protons? Is it a methyl group, a methylene group, or a methine group? We can see that there's 2 hydrogens attached to that carbon. So this is a methylene. So let's do our calculation. So we start with our methylene base. The methylene base value is 1.2 ppm. And now we're going to add the modifier effect, which is next to oxygen. Of a alcohol or ether, and that is a plus 2.5 ppm. So if we add those up, we get 3.7 ppm, and that's very close to the true value. So it's a very close approximation to where these signals would actually show up in an NMR spectrum. Okay, let's take a look at the next modifier, which is even more powerful. It is the oxygen of an ester. Oxygen of an ester, not an ether, but of an ester, and the effect there is plus 3. Let me show you an example of what that looks like. An ester, there's an oxygen, and then some hydrogens attached to the carbon next to that oxygen. Let's do our calculation. This is another methylene group because there's 2 hydrogens on that. So methylene base is 1.2 ppm. And yes, you'll need to show your work here. I want you to show out the work that you're just like I'm doing here. And then this was next to ester. And that has a value of plus 3.0 ppm. So that means these 2 hydrogens are likely to appear at 4.2 ppm, which is a very accurate approximation. Okay, and the last modifier, I'm only going to give you 3 modifiers. I don't want to make it too confusing. Obviously, there's different modifiers possible next to nitrogen, next to all this stuff, but we're not going to worry about all that. I'm just going to give you 3 modifiers. It makes it hard enough. And the third modifier is kind of mild. It's not a very strong effect, but it is important. Carbonyl, next to carbonyl group, which is a C-double-O bond. This is going to be an effect of +1 ppm. Let me show you an example of that. Let's do acetone. Okay, how about the chemical shift value of these hydrogens next to the ketone group? So that's next to a carbonyl. Okay, this is a methyl base because this is a CH3 group. So methyl. The methyl base is 0.9 ppm. And it's next to CO. That has an effect of 1.0. So our estimated value would be 1.9 ppm, which is a pretty good approximation of where those protons show up in the proton NMR. Now, it gets a little tricky because all of these modifier effects are alpha to that functional group. So notice that this is the functional group and the protons are alpha. This is the functional group, the protons are alpha. This is the functional group, the protons are alpha, meaning they're on the carbon next to the functional group. But what if they're on the carbon that's 2 away from the functional group? In other words, what if they're beta? Well, these modifiers still have an effect. It's just much lower. So this is an important fact. This is going to add a lot of complexity. This is why I'm only giving you 3 modifiers. But effect is divided by 5 for beta. Meaning these are the effects for alpha. And then there's a similar effect happening for beta. It still increases the ppm value just by a smaller amount. So for beta, I'll write those numbers in green in parentheses underneath. So plus 2.5, if you divide that by 5, you get 0.5. So the effect is plus 0.5 if it's beta to that group. Plus 3, that's going to be 0.6. And this 0.2. Okay, so those are the effects for being beta in green. We'll take a look at an example of how these effects sort of get added up together. Okay, so let's take a look at a hard example on the next page, and then we're pretty much going to be close to done with this lesson. Okay, let me draw a molecule for you, and I want you to draw it out with me. Okay, so let's say our example is going to be like this. Okay, we'll have a ketone. Okay, let's figure out how many signals this molecule is going to have, and let's figure out what the chemical shift value of those signals will be. Okay, so first order of business, I'm going to copy this molecule and I'm going to draw in all the hydrogens. So let's do that. Okay, the molecule is copied, and now let's go ahead and draw in those hydrogens. We'll draw them in blue. All right, so I just drew in all the hydrogens. Now let's go ahead and group hydrogens that are the same, in other words, they're chemically equivalent, and give them the same color. Okay, so these 3 hydrogens over on the right are clearly in their own group, so I'll call them yellow. They're all equivalent. Methyl group hydrogens are always equivalent. These 2 hydrogens here, they're enantiotopic, so they're going to give a single signal in the proton NMR, but they are unique for themselves. And then in another chemical environment, we've got these 2 hydrogens. Those are clearly unique hydrogens. They are in a distinct chemical environment. We've got this hydrogen right here, which is in a unique environment. And then what about these hydrogens here? Obviously, the methyl group hydrogens are always homotopic, right? So they're always the same in their own group. But the question is, are these protons part of this group or are they different? Well, take a look. By symmetry, this methyl group and this methyl group are freely rotating, right, around this bond. So they can interconvert by rotation. So that means that this methyl group and this methyl group are cut from the same cloth. They're in the exact same chemical environment. So they're all part of the same signal. So they're all on team green. Okay, now I know that's a tricky thing, and that takes a lot of practice to recognize that these two methyl groups are equivalent, but I'm happy to talk with you about that to help you clarify, why are those two methyl groups the same? And it has to do with the fact that this is freely rotating, so they have a chance to be in the same chemical environment. Okay, let's actually start with the green, the methyl group hydrogens. And so now what we're going to do is, now that we decided the different signals that are going to form, and we can see that each color represents its own signal. So we're going to have one signal for green, one signal for pink, one signal for blue, one signal for orange, and one signal for yellow. So that's a total of 5 signals. So now let's just calculate the ppm value for each of those signals. So we'll start with Team Green. Team Green's an awesome team. It's got 6 members in it. And so is this a methyl, a methylene, or methine? Well, these are all hydrogens attached to methyl groups, CH3 groups. So we'll start with our methyl base. And our methyl base is 0.9 ppm. Okay, do we have any modifiers for these methyl groups? Yes, we do. Are they alpha to anything? In other words, is this carbon directly attached to any of our modifiers? No, it is not. Right? So there's nothing attached to this carbon here is not a alcohol, ester, or carbonyl. However, there is a carbonyl 2 away. So there's a carbonyl beta. So we have a beta effect here. So beta to C double bond O. And what was that modifier? We look back on the other page. Beta to C double bond O is plus 0.2. Kind of pathetic, but it's still effect. So we'll go 0.2 ppm, so that's 1.1 ppm, and that's what we would expect for those protons right there. Okay. Now let's take a look at Team Pink. Okay. Team Pink. Team Pink is alpha to a carbonyl, and it's a methine, because it's just one hydrogen on that carbon. So this is the methine base. The methine base is 1.7 ppm, and it's alpha to CO, so that's going to be plus 1.0, and so the total value is 2.7 ppm for the pink proton. All right, let's do the blue protons next. The blue protons are part of a CH2 group. That's the methylene base. The methylene base is 1.2 ppm. And this methylene group is alpha to the CO double bond. And so that's plus 1.0 ppm. Any other modifiers for this blue group? Yes, it's beta to the oxygen of an ether. It has a beta modifier. It's not alpha, but so this, if the oxygen were here, it would be alpha, but the oxygen's 2 away, so that's beta. And so that's going to be beta to oxygen ether. And if you look back at this page, the beta value for being next to an oxygen of an alcohol or ether is 0.5. So add all those up together and you get 2.7 ppm. Looks like that signal may be overlapping with the pink one. Possible. Okay, Team Orange is next. Team Orange is another methylene. It's a CH2. So that's 1.2 ppm. And this Team Orange is alpha to oxygen of an ether. So that's plus 2.5 ppm. And this guy is beta to the CO double bond over on the left. So that's going to be 0.2 ppm added. Add all those numbers up together and you get 3.9 ppm as the estimated value. Okay, finally, yellow. The yellow is a methyl base. It's a methyl group. The methyl base is 0.9 ppm. And this one is just alpha to O of an ether. So that's plus 2.5 ppm. And so that's going to add up to 3.4 ppm. So we've just done something amazing here. We've taken a compound, and now we're pretty much able to predict what the NMR spectrum will look like. It will have 5 peaks in the spectrum, and the peaks will be at these approximate values: 1.1, 2.7, 2.7, 3.9, and 3.4. That's pretty cool. We are able to now predict an NMR spectrum, not just how many signals, but where those signals will be. Okay, just one more thing I want to talk about today, and then we will continue with our NMR discussion next week. The next thing I want to talk about today is something called anisotropy. Anisotropy is when nearby pi electrons create a significant induced magnetic field. So one of the most important examples of anisotropy is with benzene. So let me just try to draw a benzene on its side here. So this is kind of a side perspective angle view of benzene. Kind of crappy, I know. But just imagine like the benzene's on its side. And the hydrogens on benzene are kind of coming straight out. And remember that it's got the 3 alternating double bonds on the inside. So basically what we have is we have pi electrons on the top and at the bottom. And when we put this benzene in a strong applied magnetic field, remember that causes the electrons to start circulating, and then the molecule is going to create its own magnetic field that opposes the applied magnetic field. We talked about this in the first lesson. So if I draw the little lines, the little magnet lines, that is going to be generated by the induced magnetic field, they end up looking kind of like this, the little magnet lines. And these lines are facing in a down direction. So let me just try and do it with little red arrows to show that the direction of these magnet lines are going down. But look what happens on the perimeters, on the outside of these magnet lines. They actually face with the applied magnetic field. It's only in the center that they're opposing the magnetic field, but on the outsides, they're contributing to the applied field. So what that means is this poor hydrogen out here is in absolute hell. It's got the magnetic field from the magnet, but its own molecule is sort of betraying it and giving it an even stronger magnetic field. So this hydrogen is feeling incredibly de-shielded because it has 2 strong magnetic fields. Well, one really strong magnetic field and one weaker magnetic field, both causing it to be naked. Right? Both making it very difficult for its protons to flip, increasing the delta E significantly for that proton and making it feel very de-shielded. So this H, because of its position, relative to the pi bonds, it's getting a double dose of a magnetic field, one from the magnet and one from the molecule itself. It's got the applied magnetic field BO plus the induced magnetic field BI. So the applied and the induced. So the result of this, I mean, you're never going to have to draw a picture like this or anything. All you have to remember is that the result is H's on aromatic rings are very de-shielded. More than you might expect. They show up around 7 ppm. So that's pretty surprising. Normally, you would expect something to be around 7 ppm if it had like a lot of fluorines attached to it or something. It had a lot of electronegative atoms nearby. But in benzene, there's no electronegative atoms, but yet it's still at around almost close to 10 ppm. That means it's very deshielded, but it's not due to an inductive effect. It's due to the anisotropy effect. Okay, so that means there's a table with some special values for special protons in special situations. These sort of situations we would not be able to predict using our numbers. Instead, we would just look at the table. So here are some special values. And so we can see here, these are our friends, the methyl, the methylene, and the methine. But then we have some special situations here. We have allylic. Allylic means that it's not part of a double bond, but connected to a carbon that's connected to a double bond. So in other words, beta to a double bond. We call that allylic. And that has a rough chemical shift around 2. But again, you would not be able to predict that based on our prediction rules. Alkyne protons. Protons that are directly attached to triple bonds have a chemical shift around 2.5. Methyl groups that are attached to benzenes, those are around 2.5 as well. The protons attached to alcohols, the actual protons that attach to the oxygen of the alcohol, those are highly variable, and those appear between 2 and 5 ppm. Very difficult to predict where that shows up. So anywhere between 2 and 5 ppm, those alcohol protons can be. Now, vinylic is a hydrogen directly attached to a double bond. Those are significantly deshielded, and those protons show up between 4.5 and 6.5. Aryl protons, this is what we were just looking at the previous page, protons attached to benzene rings directly. Like, look at this. This is a methyl group attached to a benzene, but this is a proton directly attached to a benzene. That's going to have a ppm value around 7, or anywhere between 6.5 and 8. Aldehyde proton, that's a proton directly attached to an aldehyde, is 10. And carboxylic acid proton, that's a proton directly attached to the oxygen of the carboxylic acid, those show up way around 12. So if you see anything around 12, that's a good indication you have a carboxylic acid. So we can take a look at an example of a molecule like this. Okay. And so we have some allylic positions. So like, for example, this would be at 2 ppm because it's hydrogens next to a double bond. So this one down here too, 2 ppm. These hydrogens attached to the double bond directly, not one away from the double bond, those are called vinylic, and those show up around 5.5 or 6. We've got like a methyl group over here, that's just going to be at 0.9 ppm. Or I guess it's allylic too. It's one away from the double bond, so I think it's probably safer to just call that that methyl group 2 as well, because it's allylic. And then, but these guys over here are nothing. They're just regular methylene groups. So like these guys over here, they'll be like 1.2 because they're just regular CH2 groups. They don't have any of these special electronic environments. And we can also combine this table with our predictions. So for example, this compound here, we would use the table to predict the chemical shift of this hydrogen, but we could use our predictions, like alpha to oxygen, beta to oxygen, for the other part of the molecule. So you have to be smart enough to know, okay, do I know how to predict the ppm value of this proton, or do I need to use the table? And so usually you need to use the table when there's double or triple bonds involved, because our prediction rules only really tell us about if there's oxygen or CO double bond nearby. All right, so let's stop for there. Stop for here for now. Stop right here for now. And why don't you try the worksheet? There's a lot of different variety of problems there for you to experiment with. You'll start by assigning homotopic and antiotopic diastereotopic. You'll move on to predicting how many signals a compound will produce. And then finally, you will have to predict the ppm values of those signals. Okay? All right, that's it for NMR this week. And stay tuned for lab next week, where we're going to continue talking about proton NMR. And we'll also introduce carbon NMR.